Chapter 3, problem number 2 on projectile motion. Let me read the question first. A fire hose held near the ground shoots water at a speed of 6.8 meters per second. At what angle or angles should the nozzle point in order that the water land 2.0 meters away? So here's a diagram of the projectile motion. Imagine that we have a water hose with V0 as the speed of the water coming out, and I'm hitting a spot with this water. It's shooting out and going over here 2 meters away. And we call that the range. From the 0 all the way to the x is referred to as the range. Now there are two angles because I can change this angle and shoot the water higher and still hit the same spot. And I'll show you how to find the second angle once we have the first angle. But what we want to find is the angle theta to find out what angle I should set it at to hit this spot over here 2 meters away with a velocity v0. Now they give us v0 is equal to 8.6 meters per second. So let's start with our first equation of motion. This comes directly out of your notes, and you might want to read where that range equation came from. But the range equation is something that you probably need to memorize. Comes from v0 squared plus a times sine of 2 theta naught divided by g. And there is also a y max, which we're not going to use at this time, but you might want to know that for future problems. So we're going to find the range, how far, so we can find v0 x or the angle theta. So we'll start with the range equation. X equals v0 squared sine of 2 theta over g. We were given v0 to 6.8 meters per second, and we know that x is 2.0 meters. So rearranging this equation, because we want to find the angle theta, we'll write sine of 2 theta equals x times g over v0 squared. And if you know that we can take the inverse sine to get 2 theta equals sine minus 1 x times g over v0 squared. Dividing out by 2 here, we can get theta equals 1/2 inverse sine x times g over v0 squared. Now, going back to our chart and just pulling off the numbers, we know that v0 is 6.8, x is 2.0, g, of course, is 9.80 meters per second. Putting those into the equation and doing it on your calculator, 2.0 meters, 9.8, we get an angle that looks like theta is 12.53975. Again, that's too many numbers, so we go back and look at how many we were given. We have 2 significant figures here, 2 significant figures here, so we want 2 significant figures, and we reduce this to 13 degrees. That is our theta, or theta naught, the first angle of projection. Now, if we go back and look at our diagram, theta naught now is 13 degrees, and theta, the second theta, theta prime naught is equal to 90 minus theta naught. That's 90 degrees minus 13 degrees, and you should get a second angle that looks like this, 77 degrees. So that one would be 77 degrees, and those are the 2 angles we get for projectile motion.